Go ahead and drop a stone from your hand. It falls straight down, pulled by an invisible force every single time. It's simple, predictable, and feels like a fundamental rule of the universe. Now, think about this. As of mid-2025, there are more than 12,000 active satellites whipping around our planet, and that number is growing every single day. That's thousands of complicated heavy machines, some the size of a school bus, all just hanging out above our heads in the blackness of space. So why don't they just fall out of the sky like that stone? What cosmic magic is holding them up there? The answer is both way simpler and cooler than you might think, and it has everything to do with the idea of falling forever. Almost everything in our modern world runs on a silent, invisible network of machines orbiting high above us. Think about your day so far. When you checked the weather forecast, a satellite was watching cloud patterns from above. When you used your phone's GPS to find the quickest route, you were pinging a whole constellation of satellites working in perfect harmony. That live game you streamed from halfway across the world, it was likely beamed from the stadium up to a satellite and then back down to your screen in the blink of an eye. They are the unsung heroes of our connected lives, performing their crucial duties in the cold, quiet vacuum of space. But that brings up a huge question that seems to fly in the face of everything we know about gravity. We know gravity keeps our feet on the ground. It's what makes an apple fall from a tree and what pulls a baseball back to Earth after a mighty swing. The Earth's gravitational pull reaches far, far out into space, so these thousands of satellites are constantly being pulled toward our planet, every second of every day. Yet they don't come crashing down. They stay on a steady, predictable path, sometimes for decades. How is that possible? This apparent contradiction, a constant, powerful pull without a devastating crash, is what we're going to figure out. The secret isn't about beating gravity, but about using it in a really clever way. Our gut feeling about falling objects comes from a lifetime of experience. You throw a ball, it makes a nice arc, and it always comes back down. The harder you throw it, the farther it goes, but it always hits the ground eventually. So, it's completely natural to think that anything we put into space, no matter how high up, should eventually do the same thing. This leads a lot of people to the same, very logical but very wrong idea. There must be no gravity in space. This is probably the biggest misconception about space, period, reinforced by decades of science fiction showing astronauts drifting peacefully. The term zero gravity is a myth. Gravity is a fundamental force of the universe that exists between any two objects with mass. The farther away you get from an object, the weaker its gravitational pull becomes, but it never actually disappears entirely. It has an infinite reach. Let's take the International Space Station, ISS, for example. It orbits in what we call low Earth orbit, or LEO, about 400 kilometers or 250 miles up. At that altitude, Earth's gravity is still about 90% as strong as it is right here on the surface. If you could build a ridiculously tall tower 400 kilometers high and stand on top of it, you wouldn't float away. You'd feel an immense gravitational pull. So why do astronauts on the ISS float around as if they're weightless? It's because they, and the station itself, are in a constant state of free fall. Imagine you're in an elevator at the top of the tallest skyscraper imaginable, and the cable snaps. For those few terrifying seconds before the emergency brakes kick in, you and everything else in the elevator would float, seemingly weightless, because you're all falling at the exact same rate. That's precisely what's happening on the ISS. It isn't a lack of gravity. It's what it feels like to be perpetually falling. This cosmic dance between forward speed and the downward pull of gravity is incredibly precise. If a satellite's speed is just a little bit off for its altitude, things can go wrong very quickly. If it's moving too slowly, gravity wins the tug of war. The curve of its fall will become tighter than the Earth's curve, and it will begin an unstoppable spiral downwards. Eventually, it will hit the upper layers of the atmosphere, and the intense friction will cause it to burn up in a fiery meteor-like streak across the sky. On the other hand, if it's moving too fast, its own momentum overpowers gravity. Its path will start to straighten out, curving less than the Earth below it. If it reaches a high enough speed, known as escape velocity, it will just yeet itself out into deep space, breaking free from Earth's gravity entirely to wander the solar system. This delicate balance of speed and height is what allows engineers to place satellites into all sorts of different orbits, each one precisely tailored for a specific job. The most common is low Earth orbit, LEO, which is anywhere from about 160 to 2,000 kilometers up. This is the busy neighborhood where you'll find the ISS, the Hubble Space Telescope, and huge constellations of internet satellites like Starlink. Being this close to Earth is great for taking sharp, detailed pictures and for having fast, low-lag communication. The downside is that even at this altitude, the thin atmosphere still creates a tiny bit of drag, which can slow the satellite down. That's why these satellites often need to fire small thrusters to give themselves a little reboost every now and then to stay in their proper orbit. Way higher up, at a very specific altitude of 35,786 kilometers, about 20,236 miles, you'll find the geostationary orbit, GEO. What's so special about this exact spot is that a satellite orbiting here takes precisely 24 hours to go around the planet, the same amount of time it takes the Earth to spin once on its axis. The result is pure magic. A satellite in GEO appears to hover over the exact same spot on the equator, motionless in the sky. This is perfect for TV broadcast and weather satellites, because a dish on the ground can just be bolted to your roof, point at that one spot in the sky, and never have to move. In between those two is the medium Earth orbit, MEO. This is the Goldilocks zone, home to vital navigation systems like the US's GPS, Europe's Galileo, and others. Satellites here are high enough to see a big chunk of the Earth and far enough to avoid atmospheric drag, but close enough to send a strong, accurate signal to your phone or your car. You only need a couple dozen of them to provide positioning data for the entire globe. Finally, you have strange, creative orbits like the highly elliptical orbit, HEO, which are stretched out ovals. A satellite in an HEO swings in very close to the Earth on one side, picking up speed, and then flings itself way far out on the other side, where it slows down. This clever design means the satellite spends most of its time moving slowly at the far end of its orbit, giving it a long hang time over one area. This is super useful for scientific research, or for providing communication coverage over the North and South poles, which geostationary satellites can't really see. Each of these orbits is a testament to how well we understand orbital mechanics, the science of how things move under the influence of gravity. It's a field that mixes centuries of astronomical observation with some seriously complex math to make sure every single satellite stays right where we need it to be. So the next time you look up at the night sky and think about the thousands of satellites passing silently over your head, you'll know their incredible secret. They aren't fighting gravity, they're engaged in a perpetual graceful dance with it. They aren't floating, they are falling. The reason satellites don't just fall from the sky is that they are constantly moving sideways at an incredible speed. That velocity creates a perfect, delicate balance with Earth's relentless gravitational pull, a balance that locks them into a state of continuous freefall that we call an orbit. It's a beautifully simple idea that turns our everyday intuition on its head and keeps our entire modern world plugged in. Nothing is holding them up but their own speed and the fundamental laws of physics. They are forever falling, and because of that, they never, ever hit the ground. The number of satellites in orbit is exploding, with some experts predicting we could have as many as 100,000 active satellites up there within the next decade. This boom offers amazing benefits for global connectivity and science, but it also brings huge new challenges, like the growing threat of space junk and the problem of light pollution for astronomers. So what do you think about this new space race? Are the rewards worth the risks? Let me know your thoughts in the comments below. And if you thought this deep dive into how orbits work was cool, make sure to subscribe and ring that notification bell so you don't miss our next video. We'll be looking at how we use this exact same science to send probes to other planets, and how the James Webb Space Telescope uses these principles to see to the very edge of the observable universe. Thanks for watching.